Welcome back. It's Mrs. Hofferberth. Let's talk about gas law calculations. Okay, guys, it's time to do the math. Our goal is to be able to predict how changing temperature, pressure, volume, and the number of particles in a gas is going to impact the other variables. So usually we'll choose one thing that we're interested in, and we're going to see how changing everything else impacts that one variable that we're looking at. Now, these tend to be kind of intense word problems because there's a lot of things going on in them, so we need a plan. Here is the plan. First off, you're going to organize the information in that word problem into an IFI table. And I'll show you how to do this, but an IFI stands for initial. You're going to figure out what all the initial conditions were. Final, where'd you end up with? And the effect. So what effect do those changes have on the variable you're interested in? That's the first thing. That really helps break down the word problem into something much more manageable. Second, we're going to take time to really think about what those effects would be. And then once we have that, we're going to use those effects to help us create multiplication factors. And that will allow us to mathematically manipulate the variable we're interested in and calculate a final answer. Okay, one really important thing I need to tell you right now, because it comes up in these problems all of the time, is the definition of STP. So STP stands for standard temperature and pressure. And standard temperature is 0 degrees Celsius, which is 273 Kelvin. And standard pressure is 1 atmosphere. You could also use standard pressure in millimeters of mercury, 760, or torr, 760 as well. You can use it in PSI, kilopascals, whatever value for that standard pressure you want to use it. And you have a whole list of those already in your notes. So you can pick your standard pressure, but 1 atmosphere is nice. The only way to figure this out is to do a couple of examples. I'm actually going to work 3 for you, and they're going to build a little bit in complexity. That third one will have more going on. So let's read this first problem together. A gas contains 3 billion particles, and it's initially at 25 degrees Celsius and 3 atmospheres in a 2-liter container. The container is crushed, so the volume is now 1.3 liters. We're going to calculate the new pressure if the temperature and the number of particles remain the same. Okay, the first thing we're going to do is build an IFI table. Hold on just a second while I draw one of those for you. Okay, I drew you an IFI table. Let's break this down. So what you'll see along the side is the words initial, final, and effect. And pretty soon we're going to abbreviate that IFE. And then across the top are the different gas law variables: pressure, volume, temperature, and N stands for the number of particles. So the first task is to look in the problem and pull out all of the values for these different components of our problem. So we've got 3 billion particles. That's the number of particles. I'm going to write that under N as my initial number of particles. It's initially at 25 degrees Celsius. Now, here's what you must remember. I'm going to write in really big letters over off to the side here in just a second. You must use Kelvin for all gas law problems. We're talking about the motion of particles. We need to use the unit for temperature that's talking about the motion of particles. Everything has to be converted to Kelvin. So now that we've said that and written it down, and hopefully you've written it down once or twice or maybe 3 times, it's really important. Now we're going to take that 25 degrees Celsius and we're going to convert it to Kelvin. So remember, we add 273, so this is 298 Kelvin. And then we're at 3 atmospheres. Atmospheres is a unit of pressure, so that's our initial pressure. And then it's in a 2-liter container. Liters is a unit for volume, so that's our volume. So now this container is being crushed, and the volume is now 1.3 liters. So there's the final volume. And the question says calculate the new pressure. Ooh, that's what we want to know. So I'm going to put a question mark here in 2 places. I'm going to fill the column for pressure with question marks because that's what we're asked about. If the temperature and number of particles remains the same. So I can come over here and say if the temperature is the same, I know that value, just like I know the value of the number of particles. However, when something doesn't change, we're going to be able to ignore it when we do the math. So I'm actually going to just put a vertical line through those 2 columns of the table because I cannot worry about those in this problem. So there's the first step. We've got everything organized. Second step is to ask, what impact will the change have? So in this case, if we look, the volume went down. So here under the effect, I'm going to write V down because I'm making note of how the volume changed. And then I'm going to ask myself, thinking about what that means for the particles, what will that do to the pressure? Well, if I have a smaller space, there'll be more collisions, and so the pressure will increase. And so right here, still under the volume column, next to the V down, I'm going to write P up. Well, P and then upward arrow, because that's how that change in volume will impact the pressure. Once you've done that for anything that's changing, maybe there'll be more than one thing changing, but for right now there's just one. Now we're going to do the math. Okay, here's what you do. You take your starting pressure, and since that's what has the question mark, that's the top of the column you're going to look at, and you're going to write that volume, or excuse me, that pressure down. That value is the starting point for your math problem, because that's what we're going to manipulate. Next to it, I want you to write parentheses with a fraction line in the middle, because we are going to make a multiplication factor. And this is where we're going to use the numbers for volume. But we need to arrange those numbers for volume in that multiplication factor so the final answer is bigger, because when the volume goes down, the pressure goes up. So I'm going to take these two values and put them in there. And in order to get a larger final answer, I need to put the bigger volume on top. Once you have it set up this way, then you're going to take 3 atmospheres, multiply by the numerator of that fraction, and divide by the denominator of that fraction. And you will get 4.6 atmospheres. As a rule, working with those multiplication factors, if you want a larger effect, then the bigger number goes on top. If your effect is a smaller effect, so you're going to decrease the value, you want the smaller number on top. Working with this multiplication factor is something that people have a hard time with at first, so we're going to do 2 more examples, and we're going to do some practice with it in class. So make sure you're flagging and kind of making notes where you have questions, so we can talk about it when you get to class. So let's take a look at a second example. So now we've got a 5-liter container at STP, and it has 9 puffs of gas. At what temperature will the pressure of the same gas be 1.5 atmospheres? So again, you're going to start by taking this and putting all the information you know into this IFE table. So first you've got 5 liters. Liters indicates that this is volume, so I'll put that under the initial volume. And it says it's at STP. Here's where you have to recognize STP. That's standard temperature and pressure. Well, standard temperature is 273 Kelvin, and standard pressure is 1 atmosphere. And then it says I've got 9 puffs of gas. So that is my number of particles. I promise as the year goes on, we'll get a more official sounding unit for particles, but for right now, we're going to stick with puffs. The question is, at what temperature would the pressure of the same gas be 1.5 atmospheres? So at what temperature is our question, so I'll put a couple of question marks to fill that column. Would the pressure of the same gas be 1.5 atmospheres? So the final pressure is 1.5, and everything else is going to stay the same. So I'm going to draw a line so we don't worry about those. So now, not the column that has the question mark, but let's look at the pressure. So the pressure went from 1 to 1.5. So the pressure went up. We need to think about what change in temperature would accompany that. So if I need to have the pressure go up, I need more collisions. That means I need more motion, because that's what temperature does. So the temperature would have to go up as well. These are directly related to one another. So at this point, we've filled our IFE table. We've identified the effect. It's time to do the math. Remember, when you do the math, you're going to start with the value that has all the question marks underneath it. In this case, 273 Kelvin. Give yourself a place for a multiplication factor, and then use the values that are changing. So as I look at this pressure piece, as pressure goes up, temperature goes up. Since I want temperature to go up, I want to put the bigger pressure number on top. And so I'll put the 1.5 atmospheres on top and the 1 on the bottom. And then I will multiply the 273 by the numerator, divide it by the denominator, and I get 410 Kelvin for the final temperature. Let's take a look at one more example. There's a little more going on with this one. So again, we're going to start by filling out the IFE table. I see I've got 1.4 liters of gas. Liters tells me that's a volume. It's at 15 degrees Celsius, but I'm going to remember to convert to Kelvin. Okay, so that is 288 Kelvin, and the initial pressure is 800 millimeters of mercury. It's worth pointing out that in these IFE tables, it doesn't matter what unit for pressure you use or what unit for volume you use, or for number of particles, as long as you have the same units throughout the problem, but temperature always has to be in Kelvin. That one matters. Okay, this gas is compressed to 1.2 liters, so that's my new volume, and the temperature is lowered to 0 degrees Celsius, which is 273 Kelvin. And we're asked, what is the new pressure? Notice it says nothing about the number of particles, so we can assume that that's constant and not changing. Notice there's two things that affect the pressure. We have to treat each one independently when we're predicting effects. Let's look at volume first. The volume went down. If the volume went down and the box got smaller, the pressure should go up because there's more collisions. So that one should increase the pressure. Temperature went down as well. So if the temperature goes down, that means the particles move slower. There'll be fewer collisions, so the pressure should go down. Note these don't have the same effect on pressure, and that's okay. So let's talk about how you're going to do the math. Let's use our multiplication factors, and let's use them each independently. So we're going to start always with the number that's on the top of the question marks, and we're going to begin writing our math problem with that. And I'm going to do volume first. And so I'm going to set up my multiplication factor and then look at my effect. Since the volume is supposed to make the pressure increase, let's put the larger volume on top and the smaller volume on the bottom. And when you do that, you get an answer of 933 millimeters of mercury. But we're not done. Something else changed too. So take that kind of halfway done answer and multiply that partial answer by another multiplication factor for the other thing that's changing. In this case, the temperature. The temperature should decrease the pressure, so we're going to put the smaller number on top. And then when we multiply and divide, you get 884 millimeters of mercury. So we have to think about what each change will cause in terms of effects. And then we kind of do one and then the other. As you do more practice, yes, you can string this together mathematically, but starting here is a good place. Remember to be methodical. Don't try to shortcut IFE tables and gas law problems. You're just going to end up in a whole host of confusion. So take the time to make an IFE table, fill it out, think about what effect each change will have, set up your multiplication factors, and then solve. We're going to do lots of practice in class, and so make sure you bring any questions you have with you.